Welcome back to this course on multi-core architectures. The topic of this module is synchronization. It consists of 3 lessons. In the first lesson, I will describe the synchronization problem and explain why it is difficult to achieve using normal load and store instructions. In the second lesson, I will describe a synchronization instruction called test and set. And in the third lesson, I will describe other synchronization instructions. This lesson is mainly based on section 5.5 of the textbook by Hennessy and Patterson. Some slides have been based on online material. In any interesting parallel program, synchronization is required. There are many reasons why synchronization may be required. One is to order certain events. For example, if a thread needs to produce a result that another thread consumes, meaning requires as input, then they need to synchronize in order to ensure that the results are produced before they are consumed. Another reason for synchronization may be to ensure mutual exclusion. In other words, to ensure that 2 or more threads are never in a critical code section at the same time. To give an example of synchronization, here's a short example that we have seen before. 2 threads, T0 and T1, both have access to the shared variables A and flag. Initially, both A and flag are set to 0. Thread T0 first writes the value 1 to A and then sets the flag. Thread T1 does a spin lock on the flag, and as long as the flag is cleared, T1 stays in the loop. When the flag is set, it leaves the loop and prints A. Clearly, the programmer's intention is to print the value 1, albeit in a very complicated way. Here's another example that illustrates the need for mutual exclusion. Again, we have 2 threads, T0 and T1. Both of them increment the same shared variable A with 1, and A is initially 0. Looking at it from a distance, I would expect that when both threads have been executed, A should have the value 2. But is this really the case? Let's add some excitement. Hell no! Excusez-moi le mot, pardon my French. We know that the assignment A becomes A plus 1 is not executed atomically, but is translated to several machine instructions. For example, as shown here, load A into a register, increment the register, store the register value back to A. Now it may happen that before the value is stored back to memory, the other thread, in this case thread 2, the second thread, thread 1, is executed. So the order of execution may look like this, where the instructions of thread 1 are shown in blue. T1 loads the old value of A since the new value has not been stored yet. This means that T1's increment is lost. After both threads have been executed, the value of A equals 1, while it should have been 2. What can we do to ensure that such things do not happen? In other words, how can we ensure that 2 threads do not simultaneously try to update shared variables? Such situations where 2 or more threads try to simultaneously update the same shared data is called a critical section. So the question boils down to, how do we ensure that 2 threads are never in their critical section at the same time? For that, we need a synchronization primitive called a lock. A lock can assume 2 values, 0 and 1. 0 means the lock is free and that the thread can enter its critical section. 1 means that the lock is locked or set, and therefore the thread must wait. 2 operations can be applied to a lock: acquire and release. The acquire operation sets the lock and forces the thread performing the lock to wait if the lock was already set. The release operation frees the lock so that another thread may enter its critical section. Let's now look at a possible implementation of the acquire and release operations. To make the point, I'm going to sketch a wrong implementation of a lock. Here's a possible, but again, wrong implementation of the acquire operation. First, we load the lock, which is stored in memory, to a register. Then we test if the lock was set. If it was, we branch back to the beginning and try again. Then if the lock was not set, we write the value 1 into a register and then store this register to the lock variable, thereby setting the lock. Finally, we return to the caller, so the thread calling this acquire function will spin lock when the lock was set, and it will have set the lock if it was not set. At least that's what we hope. This implementation of the acquire operation is wrong. To see why, suppose that two threads call acquire at approximately the same time while the lock is free. Both will load the lock variable into a register, think the lock is free, and continue to set the lock because the store of one thread has not occurred before the load of the other thread. So both threads will think the lock is free and enter their critical sections, which is not allowed. The release operation can be implemented like this. Set the value of the lock variable to 0 and return to the caller. In this case, there is no problem, at least in most cases. Here I again illustrate why the implementation of the acquire operation is wrong. Two threads simultaneously call and execute the acquire function. Anytime before thread T0 has set the lock by storing the value 1 to it, thread T1 is executed and loads and observes the old value of the lock and also thinks it is free. Then thread 0 is executed again and also thinks the lock is free and sets it. Bottom line, both threads think they acquire the lock and enter their critical sections. On this slide, this is written in red to indicate that this is absolutely wrong. So what can be done? The problem is that the code between and including the load and the store is not executed atomically, but can be interrupted at any time. We need a mechanism to prevent this. In other words, we need atomic, meaning indivisible, read, modify, write instructions. This lesson, thanks for watching. In the next lesson, I will describe an example read, modify, write instruction called test and set. Stay tuned.